All right, so let's talk about displacement current. So before we jump into the topic, we need to understand the very few basic concept of electric and magnetic field. Okay, so if I ask you what are the process, how an electric field we can produce, so you will say that the static charges can produce electric field, and also the rate of change of magnetic flux can produce electric field. Okay, this is the two process how we can generate electric field. Now if I ask you how a magnetic field can be produced, then you will say that the magnetic field can be produced only through the moving charges or the current, because from the Ampere's law we know that integral of B dot dl is equal to mu naught ni, where the B is the magnetic field which created by the moving current, okay, or conducting current in other words. But everything was perfect until there was an experiment performed by Maxwell, and he has given the solution of this problem. Okay, so let me just give you the very basic idea how the very basic three concept we carry till date, and how they are not sufficient in describing few particular cases. For example, number one, the current creates magnetic field. That is the number one concept we have learned till date. Second, the moving charges makes current. Okay, this is the second concept. And the third one is the charge is always carried by the particle or matter like electron or proton. Now just look at this diagram. If you look at this diagram, so here as you can see there is an AC circuit connected with a parallel plate capacitor. Now when the circuit is on, when the switch is on, then the charge in the both of the plates they will vary, and basically there will be an electric field between the capacitor. Now if I try to choose two different points, for example point number one is here and another point if I choose the point is here. Now if I ask you the point one, if I ask you this one and point two, right? So if what is the magnetic field in the point 1 and what will be the magnetic field at point 2? Just pause the screen, pause the video and try to answer by yourself. I believe that you have tried. So magnetic field at the point 1 will be definitely will not be zero, because there is an current, right? So there is a current, so definitely there is a direction of the current which is flowing and the direction is changing at a particular moment. Let's say that the direction is this, and if there is a current, definitely there will be a magnetic field at the point 1. But the current, the conduction current, there is no current in between the plates, right? So definitely the magnetic field at the point 2, definitely it should be zero. But interestingly what happened is that when you place a tiny magnet over here, let's say for example over here, and a tiny magnet at the point 2, the displacement, the deflection, okay, the deflection will be almost same. For what does that mean? That means that when you place a tiny magnet at the point a and which is movable, it will deflect at a particular angle, and at the similar point if you place another magnet at the point 2, it will be deflected at the almost same angle. And this depict this establish the fact that definitely there is a magnetic field at the point 1, and the similar magnetic field is also present at the point 2. But Ampere's law clearly it is arguing with this particular point. Let's say for example if I draw an Amperean loop at the point 1, for example if I draw an Amperean loop like this, right? So this Amperian loop is going through the point 1, so definitely we can do the integration and find out the value of the B. But if I just draw another Amperian loop over here, now it's clear that no current is penetrating from this Amperian loop, so it is not possible to have a magnetic field at point 2 according to Maxwell. Okay, so that is the point of the contradiction and how this is getting solved. Just walk with me and I'll tell you what is the concept of the displacement current. Okay, let's go back to the very basic and try to look at the second line. What is written over here is that the moving charges makes current. Okay, so moving charges makes current. This is not a complete statement. What does it mean? The moving charges, definitely it makes current, but there is other things which can makes current. What is this? The change, the change in electric field, the rate of change of electric field, that can also produce current. So just let me just write down two more things. Okay, let's first write down this one. The electric field can be produced. Electric field, if I ask you, electric field, it can be produced in two way, right? Number one, if I ask you, then you will say that the static charge or charge can produce electric field. And number two, you will say that the number two is the rate of change of magnetic flux, right? So changing magnetic flux, this is another way how electric field can produce, right? This is Faraday's law. We all are aware of this Faraday's law, and we all know that how the changing magnetic field can produce electric current. But till date we only are aware of, let's say, talking about the magnetic field. Then you will say that magnetic field only, it can only produced by the electric current. Okay, so conduction current I am writing, conduction current. Is there any other option how can we produce magnetic field? No, till date there is no option of producing magnetic field. But Maxwell said, yeah, there is another way how can we produce magnetic field, and the way is the changing the changing magnetic flux can produce electric field. The changing magnetic flux can produce electric field. Similarly, the changing electric flux can produce magnetic field. And this is a major statement. When there is a changing magnetic flux, it can produce magnetic field. Now if you come back here in this diagram, then you will be able to see when there is an AC source, then at the point 2 we know that there is a changing electric flux is always there. So when there is a changing electric flux, then it is also producing some amount of magnetic field, and this magnetic field is exactly like at the point 1. So this is the exact reason why the magnetic needle was getting deflected. Now the point is that how the deflection at the point 1 is equal to the deflection at the point 2. What does that mean? That means that the value of the magnetic field at the point 1 and 2, they are exactly equal or almost equal. So also Maxwell said, one more statement, and the statement is this: the magnetic field at the point 1 and 2 are same, and also the Ampere's law is not complete. The in the next page I will discuss about the Ampere's law. Let's say, let's write the Ampere's law over here. All right. So Ampere said that the Ampere's law is this: integral of B dot dl, right? B dot dl is equal to mu naught I conduction, right? So this is the Ampere's law. All we know that. Now the point is this: the where there is no current, there is also we are experiencing magnetic field. That means this equation is not complete. Now Maxwell said this equation will be completed if we add another current with I conduction. Okay, so Maxwell said that I total, that means the total current, is composed of two current. One I conduction current, that is the basic current we know, and another one I displacement current. Displacement current, this is the sum of two current. And so he said this equation is not exactly right, but instead of this he said the equation would be written in this way: B dot dl is equal to mu naught I total. Okay, so here total means mu naught I conduction plus mu naught I displacement. Now what is this displacement current? Because let's go back to the previous slide, and here he said that, so as here there is a conduction current, and also there is another current which is flowing by the rate of change of electric flux in this direction, and he named it as ID, that is the conduction current, sorry, displacement current. Now at every place the total current is the sum of conduction current and the displacement current. For example, if we look at here, let's say for example one point is here A, one point is here at the point B, another point is here at the point C, at the point here at the point C, another point is here at the point D. Let's talk about all these 4 points. All these 4 points, all the currents, they are definitely complete, right? So I can write at the point A IC plus ID, here also IC plus ID, everywhere is I, here also IC plus ID, and also here at the point D that should be IC plus ID. All right, now interestingly at A, B and C, all the value of ID is equal to 0, right? So here only we left out with IC, and this is the value of I total. I total equal to only IC plus ID, but as ID is equal to 0 over here, then all the value is only for the IC, and also here IC, it is I total equal to, and this is also IC, this is value of I total. Okay, now at the place D, here the value of the IC is 0. That means the value of the IC at the point is 0, so that means only left with ID. Okay, only left with ID. This is very important over here. So this is only we are left out with ID, and that is the total current. And now if you look closely, then total current is sum of displacement current and the conduction current, although but at every point either the conduction current is 0 or the displacement current is 0. There is no places where they both present at the same time. All right, so if you can see C, A, B, D, all the places, only either IC is equal to 0 or ID equal to 0. Now you have all the rights to ask me why at the point A ID is 0 and why at the point D IC is 0, right? So let's talk about this and let's try to find out why these values are 0 and how can we calculate this, right? So this is Maxwell law. So sorry, this is Ampere's law and this is the correction. So let me just first do the correction, and then we'll calculate the value of the IC and ID. All right. So the correct form of the Maxwell is this. So here, let me just change the color a bit. So the value mu naught IC plus ID, in place of ID, what we can write? So in place of ID, Maxwell written epsilon naught d phi dt at the point change in electric flux. Okay, so this is the complete equation of Maxwell with that, together with the ampere. Okay, so ampere written up to this, right? And Maxwell has corrected this term. Okay, so the this current, this IC, this current, the IC is called conduction current, conduction current, and this current is called displacement current, right? Displacement current. Now interestingly, IC is always equal to ID. Okay, and more interestingly, this is equal to I total. So although I total is equal to IC plus ID, but all the places, at all the places in the circuit, either IC equal to 0 or ID equal to 0. So the equation, this equation hold true always, the this equation always hold true, that IC equal to ID equal to I total. Okay, that is the one thing that you should remember. Now I should answer your question. There are more couple of questions that is coming in my way. I know that. So the very first question is this: what is the unit, what is the unit of this displacement current? So if you look at, so if you have studied the dimension analysis, although this looks very meshy, like this is epsilon naught is there, the electric flux is there, then time is there, so this is very messy in my opinion. So if you try to find out the dimension and the unit for the displacement current, it will be very difficult. But if you have studied dimension analysis, you know that if we are adding something with something, that means they both have similar dimension and the unit. So as we are adding with IC the displacement current, definitely the IC and ID, that will be equal dimension, equal in dimension and the unit. So the dimension of displacement current, if you will be asked in the exam, that should be A, and also it is, the unit is ampere. All right, so let's move on and let's try to find out the value of the IC and ID at the various different points, and let's try to find out how the IC is equal to becoming ID. All right, so in order to do that, we need to first draw the circuit. All right. Okay, all right. So let us calculate the value of the displacement current. All right. So calculation the value of ID, okay, or displacement current. Okay, in order to find the value of the ID, we need to recall the idea or the value of the electric field for a parallel plate capacitor. Okay, we know that the electric flux is equal to the electric field dot the area, right? So this is what we already know about the electric flux. So now here the area and the electric field, they are parallel to each other, so that will be cos 0 degree, and that is 1, and that is why we can write simply EA. All right, so now what is E? For any parallel plate capacitor, we know that the value of E is equal to sigma by epsilon naught, and the value of A in this case is equal to pi small r square, right? So as you can clearly see from here, this is the pi r square, and this is the sigma by epsilon naught is the value of the electric field, right? We all know that, right? So now we want to find out the what is sigma. Sigma is the charge density, so we can write q by pi r square and pi r square over here and the epsilon naught under here. So here we can get that q by epsilon naught, that is the value of the electric flux. Now what is id? Id according to Maxwell, that is equal to epsilon naught, the rate of change of electric flux, or d phi dt. So we can write epsilon naught into the ddt of the q by epsilon naught. All right, so if you simplify this one, then you will get only dq dt. Now what is dq dt? Dq dt is nothing but ic, right? Why? Because here the ic is flowing, right? And ic, the amount of rate of change of conduction, the rate of conduction current, that will decide what is the accumulation of charge, or what is the rate of change of charge into the plate of the capacitor, right? So definitely that should be ic. So here we have proved one simple fact, is that id is equal to numerically ic. Okay, so in the very next step, we're going to prove that the magnetic field at the point P is equal to magnetic field at the point Q. All right, so here what we're going to do, we're going to find the electric field at the point P and at the point Q. So as you all know that this is a parallel plate capacitor, which is circular, that is disc form, and the P is a point at some point near the electric wire, and the Q is the point between the parallel plate capacitor. Okay, so according to Ampere's law, we know that the magnetic field at the point P, definitely that will exist, and it will follow the Ampere in loop formula, that is the B dot dl is equal to epsilon, B dot dl is equal to mu naught into I. But the Maxwell has corrected this formula, and he has written this formula in this way, that B dot dl is equal to mu naught I total. Total means that is I total current, and which is basically composed of IC and ID. IC is the conduction current and ID is the displacement current. And as we already we have discussed that at every point where there is the only the where exists at a particular moment, let's say current is flowing in this direction, and at every point in the wire, around the wire, there is only the conduction current IC, and ID is equal to 0 around here, right? Every point, let's say for example here, all that point IC exists, but ID value is 0. And what is the reason? The reason behind this is this: YD, the value of the ID, we all know that 1 by 4 pi, epsilon naught into d phi dt, right? Now what is d phi dt? That is rate of change of electric flux. Now if you consider epsilon naught, as we know that 1 by 4 pi epsilon naught, this value is equal to 9 into 10 to the power 9 SI unit. Now 1 by epsilon naught, that is 10 to the power 9. So epsilon naught is in the order of 10 to the power minus 8 or 10 to the power minus 9, which is very, very small in terms of the normal current, like 100 ampere, 200 ampere, 5 ampere, 10 ampere, right? This is very, very small. So this ID is almost 0 around all these conducting wire. But there is the valid value of the IC is there, but at the place of point Q, we know that here the IC is 0, where the space between the plates, of the capacitor. Okay, this is the capacitor plate, we all know, right? This is the capacitor plate, we know that, and the space between this, we have drawn a kind of pink color. This is the only space, vacuum we can consider. So the space between this is the IC is 0, definitely we know that, because no charge is flowing and carrying current. But the ID, the value of the ID, there is only existed value of the current is ID. Okay, and already we have discussed that the how IC equal to ID. If IC equal to ID, then we want to find out the magnetic field at the point P and magnetic field at the point Q, right? So let's do it. Magnetic field. Okay, so you have to find that, let's say magnetic field at the point P. Magnetic field at the point P. Okay, so here what we're going to find that, let's say, yeah, so how can you find that? Using the Ampere's law, right? So that is B dot dl is equal to mu naught according to Ampere Maxwell I total, right? So that is equal to mu naught IC plus ID. But as the ID value is 0 around any conductor, so that value only mu naught IC. All right, so now here B dot dl, as we can clearly see that the B will go outside, integral of dl is equal to mu naught IC, and integral of dl will tends to be the 2 pi capital R. So 2 pi capital R is equal to mu naught IC. So B, the value of the B magnetic field, is equal to mu naught IC by 2 pi R. Okay, so this is the value of the magnetic field. All right, so let's square this out. You done. All right, so let's highlight this thing, little tiny little formula we have learned. So now from the very beginning we are discussing about the fact that the magnetic needle deflection of the magnetic needle at the point P and Q is equal. So the magnetic field at the point P and Q should be equal. Let's find out whether the magnetic field at the point Q is equal to the magnetic field at the point P or not. All right, so let's do it. So let's find out the magnetic field at the point Q. All right, so let's highlight this thing. Okay, all right, so in order to do that, what you can do that we should write the Amperean formula, right? So Amperean formula is this: B dot dl is equal to mu naught I total, right? So that is equal to mu naught I total means IC plus ID, right? And here IC is 0, only ID is there, so I should write mu naught ID. All right, so now here as you can see that B dot dl, if you consider the value of the B dot dl, so in this case the integral of dl, if we consider, because P and Q, they definitely have the same radius, right? So in this case what we can consider that the value of the B dot dl, that should be is equal to, B will move outside, integral of dl is equal to mu naught ID, and next we can write that B into 2 pi R is equal to mu naught ID, and that is equal to B equal to mu naught ID by 2 pi capital R. Now as we already have discussed that IC equal to ID, so this formula will leads to B at the point Q is equal to mu naught IC by 2 pi R. Okay, so let's square this thing out. Okay, so now what you can do is highlight this thing. Okay, so this is what we wanted to find out. The value of the magnetic field is exactly equal at the two different points, that is at the point P and at the point Q. So here I should write P, BP, okay, and here BQ. Okay, so they're equal, and that's why the magnetic needle was showing the same deflection. Yeah, that is what we wanted to derive in this particular video. All right, thank you so much.